I'll go back to studying. I'll go back to studying once I finish checking my phone. What is this post? It says that all carbon fiber disappeared in the world.
Yeah, apparently all the carbon fiber disappeared.
Yeah. Oh, what can happen?
I'm not sure. Let's find out.
Hey, do you have any plans for a break?
No, I was just gonna go home and travel. But do you?
I think I'm gonna go home as well. Take a plane ticket home.
What type of plane ticket?
Let's see. Hey, why are the plane tickets so expensive?
Because carbon fiber disappeared.
I think I need to take some money out of my bank account.
Speaking of which, I need to check my stocks. Since carbon fiber's missing, I think everything disappeared. Yeah, all my stocks went down.
How's your Tesla stock doing?
It crashed.
This is so messed up. I'm going back to sleep. Screw studying for finals.
Good night. Hey, wake up.
Huh? What happened? Wait, what happened to all the carbon fiber?
What carbon fiber?
Didn't it all disappear?
No, you're just delusional. Yeah, but we have a final in like 2 minutes.
Oh, shoot!
So what is it? Carbon fibers are a polymer of dense strands of carbon atoms that are binding together to form a crystalline structure and create a material that is lightweight and strong. The crystalline structures are binding together to form a chain-like structure that is resistant to stress and stretching that is 5 times stronger than steel and twice as stiff at a lighter strength-to-weight ratio. Carbon fiber can be molded into any shape and can be hardened through a process called curing, resulting in a lightweight, rigid material. Additionally, carbon fiber undergoes additional treatments for specific requirements that can be combined with other hybrid composites that can form the durable materials that we know carbon fiber to be, especially for aircraft and other specialized industries. The history of carbon fiber. In the 1800s, Joseph Swan would produce carbon fiber for the first time to be used in a light bulb. Thomas Edison would later adapt this technique in the incandescent light bulb by heating cottons or bamboo at high temperatures and carbonizing them into carbon fiber filaments. In 1958, Roger Bacon would create a high-performance carbon fiber and union carbamide by heating strands of rayon until they are carbonized. However, this process would soon be inefficient as the fibers only contain 20% of carbon. However, this would cause Dr. Aoko Shindo in 1960 at the Agency of Industrial Science and Technology of Japan, using polyacrylamide nitrile or PAN, that his fibers would contain only 55% of carbon. This would later be improved by Richard Mullington of H.I. Thompson Fiberglass Co., and he would produce a 90% carbon fiber using rayon as a precursor with PAN fibers. This fibers are later reused for what is known for our aircraft and vehicles and other industrial usages. In the 2000, newer carbon fibers would contain 95% of carbon with an increased tensile strength and elasticity. Modern carbon fibers are mass-produced and are used for industrializations for its lightweight, durability, and strength to be known to be stronger than steel.
Carbon fiber is produced by processing organic polymer raw materials known as precursors. There are mainly two types of precursors, PAN and petroleum pitch. There are other types of precursors like rayon, which is used in the earlier days. PAN-based carbon fiber is manufactured through five main steps: polymerization, spinning, thermal stabilization, carbonization, and surface treatment. First, acrylonitrile is mixed with the catalyst to produce a polymer called polyacrylonitrile, or PAN. This polymer serves as the precursor for the carbon fiber. Next is the spinning process. The polymer is extruded through extremely small nozzles to form thin fibers. Wet spinning is the most commonly used method. During this stage, the fibers are washed and stretched, which helps align the internal molecular chains and achieve the desired fiber diameter. The fiber then undergo thermal stabilization. They are heated at about 200 to 300 degrees Celsius for 30 to 112 minutes in the presence of oxygen. During this process, oxygen is absorbed and the linear molecular chains rearrange into a heat-resistant ladder structure. This step is important because it prevents the fibers from melting during the next high-temperature stage. After stabilization, the fibers go through carbonization. They are heated to very high temperatures, typically between 1,000 and 3,000 degrees Celsius, in a nitrogen atmosphere. During this process, non-carbon atoms such as hydrogen, oxygen, and nitrogen are released as gases, leaving mostly carbon atoms behind. These remaining carbon atoms then bond together and form a crystalline structure that aligns parallel to the fiber axes. This alignment gives carbon fiber its high strength and stiffness. Finally, the surface of the carbonized fibers is slightly oxidized to increase surface roughness and chemical reactivity. This improves the adhesion between the carbon fiber and resins such as epoxy when the fibers are used in composite materials. Manufacturing pitch-based carbon fiber follows slightly different process. It follows 5 main steps including pitch preparation, melt spinning, oxidative stabilization, carbonization, and surface treatment. Pitch-based carbon fiber production begins with the removal of impurities. Pitch, which is derived from petroleum or coal tar, contains solid particles and gel-like impurities. These impurities must be removed because they can reduce the tensile strength of the final carbon fiber. After pitch is prepared, it goes through the spinning process. Since pitch melts when heated, melt spinning is used to form fibers. For mesophase pitch, fibers are typically spun continuously at around 350 degrees Celsius. The shape of the spinneret holes can also be adjusted to control the cross-sectional shapes of the fiber. Next, the fibers undergo oxidative stabilization at around 200 to 300 degrees Celsius. This step converts the thermoplastic pitch into an infusible thermal setting structure so that the fibers do not melt during carbonization. If stabilization is insufficient, the fibers may melt during carbonization, while excessive stabilization can degrade mechanical properties. Pitch-based fibers have very high carbon yield, about 80%, which is higher than pan or rayon precursors. The carbonization step, however, follows the similar carbonization step used for pan precursor. It is heated at higher temperature at around 1,000 to 3,000 degrees Celsius in nitrogen atmosphere. In addition, pitch molecules naturally align along the fiber axes during spinning, allowing high performance to be achieved during carbonization without applying large tensile stress. Finally, after carbonization, the fiber surface is oxidized to increase surface roughness and chemical reactivity. The fibers are then coated with a protective sizing layer and wound onto cylinders called bobbins.
What is carbon fiber used for? Before we talk about its applications, let's first talk about why is carbon fiber used. First off, carbon fiber is extremely strong, being 5 times stronger and 2 times stiffer than steel. It is also extremely lightweight, making it have one of the greatest strength to weight ratios of any material. Additionally, carbon fiber is resistant to corrosion and has very high stiffness, meaning it does not easily bend or deform. Because of these properties, engineers use carbon fiber when they need materials that are both strong and light. Now let's move on to some of the applications of carbon fiber. First, we have aerospace applications. Modern aircrafts use carbon fiber composites in the fuselage, wings, tail, and control surfaces, and interior and structural components. In modern aircrafts like the Boeing 787 and Airbus A350, carbon fiber makes up 50% of the airframe. This is because carbon fiber is much lighter than traditional metals like aluminum and steel. It reduces the overall weight of the aircraft. A lighter aircraft uses less fuel, which improves efficiency and lower costs. And that is why that darn plane ticket was so expensive. Another advantage is that carbon fiber has great fatigue resistance, meaning that it is much more resistant to weakening over time, which increases the lifespan of aerospace components. Carbon fiber has also become one of the most important materials in modern sports equipment. This is because it provides a combination of high strength, low weight, and high stiffness. These properties allow athletes to generate more power and control while using lighter equipment. For example, tennis rackets made from carbon fiber are very stiff, which means they bend less during impact with the ball. Because of this, more of the player's swing energy is transferred directly into the shot, increasing both power and accuracy. In bicycle frames, carbon fiber is used because it is extremely strong but significantly lighter than metals like steel or aluminum. This reduces the overall weight of the bike, which improves acceleration, climbing efficiency, and overall speed. Finally, golf clubs, particularly drivers, often use carbon fiber shafts or composite club heads. The reduced weight allows golfers to swing faster, which can increase the distance the ball travels. Carbon fiber is also widely used in the automotive industry, especially in high performance and racing vehicles, where reducing weight while maintaining strength is critical. One example is Formula One racing cars. The main structure of a F1 car is called a monocoque chassis, which is made almost entirely from carbon fiber reinforced composites. This structure acts as a protective shell around the driver. Despite being extremely lightweight, it is incredibly strong and designed to absorb large amounts of energy during a crash, helping to protect the driver. Carbon fiber is also commonly used in supercar body panels, such as those found in sports cars. Because carbon fiber is much lighter than steel or aluminum, it reduces the overall mass of the vehicle. Lower vehicle weight improves acceleration, braking, and fuel efficiency. Another advantage of carbon fiber in cars is its high stiffness. Stiffer materials reduce flexing in the chassis and suspension components, which improves handling and vehicle stability, especially at high speeds. Carbon fiber also has applications in medicine. One of the most important applications is orthopedic and spinal implants. Carbon fiber is strong, lightweight, and radiolucent, which means it doesn't block X-rays or CT scans. This allows doctors to monitor bone healing, spinal alignment, and post-operative recovery more clearly. Another key advantage is that carbon fiber has a stiffness similar to natural bone, which reduces stress differences between the implant and the body. This helps prevent bone weakening and makes the implants work more naturally with the patient's skeleton. It is also used in prosthetics. The low weight and high strength of carbon fiber makes prosthetic limbs more comfortable and natural to use. Amputees can move faster, perform daily tasks more easily, and experience less fatigue, improving their overall quality of life. In radiology equipment, carbon fiber is widely used for frames, supports, and imaging tables. Because it's X-ray friendly, it doesn't interfere with scans, allowing for clearer images and more accurate diagnoses.